let's talk about partial derivatives. A partial derivative can be calculated by treating one of the variables like a constant and differentiating with respect to the other one. Later on in this video, we need to rigorously define what we mean when we say partial derivative. But for right now, let's just practice taking a partial derivative of f of xy equals x squared plus y squared, thinking of a partial with respect to x as the derivative found by differentiating this equation, treating y as a constant. And as I read this definition, we pick up new notation. We can't call this df dx. We're not differentiating the function with respect to x because there might be a relationship between x and y that we're completely ignoring by treating y as a constant. So there's this new symbol. And this symbol is literally the symbol of the partial derivative. It is not a Greek letter. It is not any kind of letter. It is literally a symbol that was made up for this purpose. All right, well, not too hard of a problem here. We're asked to take the derivative with respect to x, treating y like a constant. Well, if y is a constant, then y squared is a constant, and when I take the derivative, that goes away. Derivative of a constant is 0, and then the partial with respect to x would be 2x. Now again, we need to define this rigorously so we understand what's going on, and we need to understand what's going on visually when we think of a partial derivative. But there's my partial with respect to x. Well, if you can have a partial with respect to x, you can have a partial with respect to y. Partial of f with respect to y can be thought of as the derivative found by differentiating with respect to y, treating x as a constant. Well, in this one, if x is a constant, x squared is a constant, and we get 2y. So pretty simple examples. The partial with respect to x was 2x. The partial with respect to y is 2y. Let's look at a different example. So let's imagine I have f of xy is the top half of the unit sphere. Not drawn particularly well there. Let's calculate both partial derivatives, the partial with respect to x and the partial with respect to y, and then see if we can interpret that visually. So first I need to take the derivative treating y as a constant. This will be my partial of f with respect to x. Well, think of the square root as a 1/2 power, so I have 1/2, leave the inside alone, to the minus 1/2, and then I need to multiply by the derivative of the inside, which would just be minus 2x. So I'm differentiating with respect to x, treating that y as a constant. All right, well, we can simplify this. The 2 and the minus 2 reduce nicely. I have minus x all over the square root of 1 minus x squared minus y squared, and there's my partial with respect to x. Pause the video here and calculate the partial with respect to y on your own. Okay, well, if you follow that same procedure, the first bit will look the same, but that will become a minus 2y when you use the chain rule. So we'll end up with a minus y over the square root of x squared, 1 minus x squared minus y squared. And there are my two partial derivatives. Well, I have a graph here, and these definitions should have something to do with something going on in this picture. Well, let's think about the partial with respect to x. That is calculated treating y like a constant. So let's treat y like a constant. I'm just going to call that constant y naught, right? Some value of y. Well, I could actually imagine plugging that in and having a function on one variable and taking the derivative, and I'd get exactly what I have here if I plug the value y naught in for y. Well, if I think about all of the points in space with an equation y equals y naught, that would give me a plane that's parallel to the xz plane. I could then think about the curve traced out on my hemisphere in that plane. That curve would be a semicircle. I didn't do a great job of drawing it there. but that curve would have a slope, and I could actually think about every point in that plane as being an ordered triple that is an x, a y naught, right, a fixed value of y, and a z. Since y naught's fixed, I could actually treat that very much like I would the xz plane, and I could imagine this 2D curve as having an equation in x and z, a relationship between these two variables, because I know the y is fixed. And then this becomes the derivative formula. This is actually going to tell me the slope in that fixed plane of every point on that curve. So now, if I take an actual value of x naught and plug it in there, I'll get the slope of this tangent line. So the slope of this tangent line would be the partial of f with respect to x evaluated at the point x naught, y naught. Because I was treating y like it was fixed, this formula works for any value of y. All I have to do is plug in the x. In the same way, this formula is calculated treating x like a constant. So I could imagine fixing a value of x maybe back here. Again, that would give me a plane, this time parallel to the yz plane, and I'd trace out another semicircle. If I plugged in an x naught to this formula, if I plugged in a y naught to this formula, then I would get a tangent line. So these partial derivatives are still giving me slopes of tangent lines. So we still need a rigorous definition, and we still probably need to do an example where we actually find one of these slopes. But that's it for now.